What's up? This is Mario and welcome to Awesome Acoustics. In this video, we will look at what is sound physically, what are its characteristics such as frequency and amplitude, and how these characteristics relate to our perception of sound. The physical phenomenon of sound will always begin with an object vibrating mechanically. A musical instrument, your vocal folds, a loudspeaker, etc. Here, I will use the example of a bell. When a bell is vibrating, it will carry out tiny movements forwards and backwards, pushing and pulling the air particles just in front of it. When pushed, those particles push the next ones, and those push the next ones, and so on. When pulled, those particles will pull the next ones, and those will pull the next ones, and so on. This chain reaction that propagates through the air is, fundamentally, a sound wave. A small technical clarification is that when talking about air particles, I don't mean individual molecules, since molecules already have their own random vibration due to temperature. So, in this context, a particle means a group of molecules large enough that their random vibrations due to temperature average to zero. But it is still a small enough amount of air that we can still imagine it as a tiny dot of air. In the context of acoustics, when we talk about vibration, we're talking at the particle level. In the bell example, sound would actually propagate in all directions, but to make this easier to visualize, let's look at propagation in a single direction. Here, the dots are air particles, and what is shown is a piston vibrating inside a duct producing sound waves. However, this animation is in slow motion for visualization purposes. Within the human hearing range, this animation would be between 80 and 80,000 times faster. The way the air particles move look like ocean waves when looked from above, don't you think? To be able to study sound, it is important that we talk about pressure, since the variation of pressure is what we can measure with microphones. Atmospheric pressure is basically the weight of kilometers of air pushing down on a surface, or on your own shoulders. If you climb to a higher place, you'll have less air pushing down on you, so atmospheric pressure would be lower. Pressure is measured in a unit called the Pascal and equals exerted force over surface area. At sea level, atmospheric pressure is this much. Mexico City is one of the highest capital cities in the world, at an altitude of 2.24 kilometers above sea level. At that altitude, this is the atmospheric pressure. Where you live, atmospheric pressure is surely somewhere in this range. In air, as in any medium, molecules are naturally separated by a certain distance. If you try to compress the medium, molecules will try to push away from each other, exerting an outwards force and therefore a pressure. In the same way, if you stretch the medium, it will exert an inwards force, trying to return to its original density, kinda like rubber but at a tiny scale. This produces a negative pressure. When you have a vibrating object, it will cause compressions of air, which are the regions where particles are pushed together, and expansions of air, which are the regions where they are pulled apart. Where air compresses, pressure increases, and where air expands, pressure decreases. These high and low pressure regions propagate through the air. That is, when there's a sound wave, the pressure in a position in air will slightly oscillate above and below the atmospheric pressure. If there is no rapid variation of pressure, there is no sound. Another important thing to mention here is that, although sound waves do propagate, air particles do not travel long distances, but only oscillate around their point of balance. We can easily see this on the red dots. Typically, when we think about a sound wave, what we imagine is the drawing below. However, this is only a graph, or a plot, that helps represent what is happening in the animation above in a simpler way. Here, the vertical axis represents pressure. That means that the higher the curve is, the higher the pressure, and the lower the curve is, the lower the pressure. Here, we can see that the upward peaks are synchronized with the high pressure regions. Upward peaks are also called crests, and downward peaks are called troughs. Crests show the maximum pressure, troughs show the minimum pressure, and the central line represents atmospheric pressure. If we subtract atmospheric pressure from these three values, what we now have is a positive pressure, a negative pressure, and 0 on the central line. This is the most common way of representing sound waves, and negative pressure will typically be the same as the positive pressure, only negative. When we talk about the amplitude of a wave, we're talking about how large it is in the vertical direction. So the first wave has a low amplitude, and the second one has a high amplitude. Amplitude is directly related to the loudness of the sound we hear, or as we say in common speech, the volume. In a wave, a small amplitude would correspond to a weak sound, while a large amplitude would correspond to a loud sound. There are several types of amplitude, but the most important ones are peak amplitude, RMS amplitude, and instantaneous amplitude. Peak amplitude is the vertical distance from the central line to a peak, and it is typically considered positive regardless of whether you measure it towards a positive peak or a negative peak. For example, here sound pressure goes from minus 0.5 Pascal to 0.5 Pascal, so the wave has a peak amplitude of 0.5 Pascal. However, the wave is not always at this value, but it is only the maximum. It might be more useful to find something like the average of the whole oscillation. This is what we use RMS amplitude for. The acronym RMS means root means square, because to calculate it, first you square all of the wave's points, then get the mean, and then get the square root of that value. Quick reminder, mean is the same thing as average. But then, why bother with the root and the square if we could just calculate the mean? Well, if we only calculate the mean, we would be adding the positive and negative parts together, and the result would give us 0. Squaring all the values makes the whole wave positive before calculating the mean. Additionally, this specific way of getting an average pressure is more related to our perception of loudness, compared to simply calculating the mean of the absolute values. When we have sine waves, meaning that they have this exact shape, then the peak amplitude and the RMS amplitude are related to each other through the square root of 2. This is a fact that's worth keeping in mind, since most of the time you'll be dealing with RMS amplitudes of sine waves. Something very important is that sound pressures are typically expressed in RMS amplitudes, not peak amplitudes. For example, a 1 Pascal wave actually has an RMS amplitude of 1 Pascal and a peak amplitude of 1.4. That is, pressure varies 1.4 Pascal above and below atmospheric pressure, which let's recall is a number within this range. However, such a tiny variation over atmospheric pressure is already a considerably loud sound. Last, we have instantaneous amplitude. This is the vertical distance between the central line and any point in the curve, not necessarily a peak. In this case, the direction of the line is considered, so an instantaneous amplitude going downwards would be negative. Another unit used to measure sound amplitude is the famous decibel. However, this is a unit for which I want to dedicate a whole video to explain it in detail, so I'll address it in the next video. The next characteristic of a wave that we can see here is wavelength. A sound wave is periodic, that means its vibration pattern is repetitive. A wavelength would be the physical distance, measured in units like meters, between two identical points in this pattern. A wavelength is a consequence of two things: speed of sound and frequency. Speed of sound is not a fixed number. It actually depends on many factors, the main one being the medium through which sound is propagating. Typically, we think of air, since that is the medium through which it arrives to our ears. However, sound can also propagate through other media, like water or metal. And typically, the more solid the medium, the faster sound travels. For example, these would be ranges of speed of sound in these three media. Sound waves always need a material medium to propagate. In the middle of space, far away from planets and stars, there's practically no physical matter, so sound cannot propagate. Here, the solution is to transmit the sound in the form of electromagnetic waves, which do not need a material medium. But, close to planets and stars, there may be gases that serve as a propagation medium. Other factors that affect the speed of sound are the temperature of the medium and its humidity. For example, sound travels faster in hot air versus cold air, also faster in humid air versus dry air, although in this last case, the difference is very small. This is why when we talk about the speed of sound, we have to say, the speed of sound in dry air at 20 degrees Celsius is... and then we say that it's typically 343 meters per second. Translating this to a perhaps more familiar unit, this is approximately 1235 kilometers per hour. The speed unit Mach is defined relative to the speed of sound. So, a speed of Mach 1 would be 1235 kilometers per hour, and Mach 2 would be twice that amount. Now, frequencies. If you already know a little bit about sound and waves, you'll surely think of frequency as how rapidly a wave vibrates. But I want to really emphasize that the concept of frequency is actually more general than that. Frequency simply means how often a repetitive event, whatever it is, happens in a unit of time, where the frequency is constant across several units of time. The frames per second in a video camera, the beats per minute in a musical composition, and how often it is Friday throughout the year are all technically frequencies. The standard measurement unit for frequency are the hertz, abbreviated this way. Hertz means repetitions in a single second. There are two ways to determine a frequency in hertz. The first one is literally counting how many repetitions happen in a single second, but the hard part would be determining the decimal digits in case the interval is not an exact fraction of a second. The second way is much more reliable. It consists on first measuring the interval between two consecutive happenings in seconds with all the decimal digits you need. This is called its period. Then, if you take the period and divide 1 over that quantity, voila, we have a frequency in hertz. In the same way, 1 divided by the frequency gives us its period. Let's try the first method. Listen to the following rhythm, and with the help of this clock, we will figure out the rhythmic frequency of the sounds. In this rhythm, there are exactly 2 sounds per second. Therefore, its rhythmic frequency is 2 Hz. If we use the second method, then we will measure the interval between each sound. Here, we find that the interval, that is, the period, is 0.5 seconds. And if we divide 1 over 0.5, we arrive to the same 2 Hz. If we have a somewhat stranger rhythm, and we count the repetitions with this first method, this will give us a rounded number, which can be inaccurate. But the second method gives us a more precise number. For example, here we have intervals of 0.64 seconds. That is, the frequency of this rhythm is 1.5625 Hz, which would have been very hard to determine with the first method. Bringing back a couple of examples I mentioned earlier, it would be the same thing to talk about a camera recording at 60 frames per second than saying it takes captures at a frequency of 60 Hz. Or we could convert the beats per minute in a musical score to beats per second, so that in a composition with a tempo of 120 beats per minute, its beats would have a frequency of 2 Hz. Now, when we talk specifically about waves, and I mean any kind of wave, with frequency, we mean how many times the vibration pattern, or cycle, of the wave repeats in a single second. The wave will not necessarily have this shape, but it can have different shapes, as long as it repeats in the same way. I'll talk more about that a bit later. For example, if we have a sound wave where the pressure has 5 complete oscillations in a single second, then it is a 5 Hz wave. However, for human perception, this is a very low wave frequency, so low that we actually can't even hear it. The ear of a young, healthy person can typically hear frequencies in the range of 20 Hz to 20,000 Hz. As we grow up, this range diminishes, so that a middle-aged person typically cannot hear above 14 kHz. This may sound like they have lost more than a quarter of their hearing. However, hearing is logarithmic, so this loss is not as bad as it seems. I will explain the concept of logarithmic in the next video. The frequency of a sound wave determines its pitch, so how low-pitched or high-pitched a sound is when we hear it. Low frequencies are associated to low pitch, and high frequencies are associated to high pitch. Just as in the previous examples, we can obtain the period of the wave by dividing 1 over the frequency. Or we can also measure the time between two identical points in the wave. Now, here there might be a little bit of confusion, because so far we have called this distance between 2 points in 2 different ways: period and wavelength. What is the difference, and how do we distinguish from one another? Period has to do with time, while wavelength has to do with physical distance. So, it depends on what you are showing on your horizontal axis. If you are showing time, then what we can measure is its period. If you have position or distance in meters or a related unit, then what we can measure is its wavelength. As I mentioned before, wavelength is a consequence of speed of sound in a medium and frequency. A sound wave will always propagate in the same medium at the same speed, regardless of its frequency. So, if the object vibrates with a higher frequency, then the distance between two identical points in the cycle will be shorter. Wavelength can be calculated with this formula. The wavelengths in dry air at 20 degrees Celsius would be 17.15 meters for 20 Hz and 1.715 centimeters for 20 kHz. When you make these calculations, make sure to always use standard units. For example, speed of sound must always be in meters per second, and never in derived units like kilometers, miles, or hours. Also, if we compare sound in air versus sound in water, wavelengths in water will be larger for the same frequencies than in air, since sound travels faster through water. A very interesting effect that we can now understand is the Doppler effect. Basically, it is the effect that happens when a car passes in front of us, and what we hear is... Again, this has to do with sound propagating through the air at a constant speed. If the sound source is moving forward, this will reduce the wavelength, so when it arrives to our ear, it will be as if it had a higher frequency, so a higher pitch. In the same way, when the source moves away, this increases the wavelength. Then we perceive it with a lower frequency, so a lower pitch. The real sound that the car is emitting is the one that we hear as it passes right in front of us. Let's listen to the example again now that we can understand the effect. Okay, so far we have talked about sound waves that repeat indefinitely, but another characteristic of sound is duration. This is as simple as when it starts and when it ends. Finally, I want to talk about waveform. The form of a wave determines its timbre, which is the characteristic that allows us to distinguish between different musical instruments, different people, or other objects that produce sound. Well, actually, it is more correct to say that the frequency spectrum of a sound is what determines its timbre. But that is a slightly more advanced topic that I will address in another future video. It is still true that each instrument, person, or object produce a characteristic waveform, and for now, the waveform approach is simpler. The concept of timbre is a bit more abstract than the previous ones we have talked about, but the easiest way to think about it is like this. If pitch is the characteristic that allows us to distinguish between two musical notes played by the same instrument, timbre is the characteristic that allows us to distinguish between two instruments playing the same musical note. A simple example is when listening to these synthesized waves: a sine wave, a square wave, and a sawtooth wave. Keep in mind that the musical note is the same in all three examples, and even then, each wave sounds different. These waves are very easy to produce electrically, so they are sounds very classically used in synthesizers. For example, the melodies produced by an old NES console are mainly square waves. It also has a triangular wave channel for the bass notes and a fourth channel that produces short noises to emulate percussions. In the real case of a musical composition or a person speaking, all of these characteristics are not fixed, but are varying with time. In order for you to get an idea, this is what this video's audio looks like when zoomed out, and this is how it looks when I zoom in. Another example that I'm honestly in love with is this visualization of the main theme of The Legend of Zelda for the NES, where you can see all the concepts explained in this video in action. The different waveforms that produce different sounds, the periods that become shorter when producing higher musical notes, the amplitudes that change to give a higher impact at the beginning of each note. You can even see when the note is doing a vibrato, the wave slightly vibrates horizontally. This is because a vibrato is a small variation of frequency. Here, I will only show a fragment, but I will leave a link to the original video in the description. With that, we conclude this episode, and in the next one, we will talk about the decibel. See you soon!